Okay, good afternoon to everyone. So today class we will see the recap of Unit 3. Okay, so once again very quickly we will see the controller design, discrete controller design, and the same we will try to simulate in the MATLAB. Okay, just is an example how we can do any work related to the digital control system. Okay, so all the topics is known to you. Just I will go through fast. So discrete controller design, and today topic is discrete controller design. So this is a control system, right? So all these things we know. So it requires a set point and difference input, and we are going to calculate the error. Okay, the error is going to provide at the controller. So our interest is to design the controller block. So this is our D object. Okay, the controller output is given to the process system, which are going to be controlled. That is nothing but input to the system. The process may be anyone: aircraft, missiles, process industries, manufacturing industries, automobile. It may be anyone. Okay, and the output nothing but the information carried from the process. So it should track the difference input. So desired performance. Our objective is the output should track the difference input and error will becomes as small as possible. Okay, so ఇక్కడ key issues ఏంటి? Practical implementation. We are seeing now the practical implementation of these algorithms. So how to describe the system to be controlled. Okay, then how to design a controller. That means first one, modeling of the process. So you need to know entire the knowledge about the process via mathematical modeling. If you know exact the mathematical modeling of the any process, then you can easily describe the system transfer function either in time domain or in continuous domain or in discrete domain. Okay, if you know the model, then you have to go for the design of controller. Okay, so controller may be anything. What we have learned: Dahlins, Deadbeat, Kalman. Okay, so you have to use any controller. You can use any controller, PID. Okay, so there's no restriction on the type of the controller. So first you should know the modeling of the process. These are the key issues if it comes to the real-time implementation of any control algorithm. Okay, ma, మీకు ఏమైనా doubts ఉంటే you can ask it any time. And this we already seen. Okay, so I have explained during the introduction part of this unit. So we have various inputs as a plan. Okay, plan, sensor, actuator, computer, communication. All these things will be acting as a physical process. Okay, so we are going to obtain the mathematical modeling by using these techniques: differential equation, or you can apply the Laplace transform. Okay, once you have the equation in this form, then easily you can get the transfer function or state space representation. So these four are related to the continuous time. Similar way you can extract the mathematical model in the discrete domain, so by using difference equation and jet transform method. Okay, so this is nothing but the continuous domain, and this is nothing but the discrete domain. Okay, so once you have the model, then you need to go for the system analysis. Right? So system analysis means you have to apply this technique: root locus, Border plot, Nyquist plot, okay, or stability, robustness. These are all parameters under the analysis of the system. Now, if you know these three, once you know these three, then you can go for the controller design based on the previous knowledge about the process. Okay, the controller may be estimator, it may be identification or regular tracking, set point tracking, servo response, PID, pole placement, optimal control, adaptive, robust, decentralized control. We have n number of control design techniques. Okay, so if you want to apply any controller to the system, so you should know these parameters. Okay, so these are generalized. We already know about these things, and we will see how you are going to apply reference input in discrete domain. So here you are going to sample the signal with respect to time t. The input signal is provided in continuous domain that has been sampled with respect to time t. Okay, so the output also already sampled with respect to time t. Then no need to sample the error signal. Error signal directly can pass to the system. Okay, the output of the errors controller will be in the form of discrete. Will be in the form of discrete. So E object will be in the form of discrete. So that should be reconstruct in analog mode by using the ZOH. So the output of ZOH is nothing but the analog mode and process transfer function. So this is the process. So we are going to provide analog signal to the process. Okay. So this is the way of representation of discrete time system with respect to analog reference input. Now I am changing the analog signal into the discrete domain. Then what will happen? R of Z is replaced with R of Z. Okay, and rest of the things will be same. Okay, so R of S alone replaced with the R of Z. You may ask why the output equation, that means Y of S, has not been replaced with Y of Z, because it's a continuous process. Okay, the output from the process is nothing but analog mode that should be sampled always continuously, okay, to get the corresponding discrete time signal. Okay, ma. So we can't replace Y of S with Y of Z. Always the feedback element should have the sampler. Feedback element should have the sampler technique. Okay, so this is one of the bit mark question, and you will get in during competitive examination. Everything we can replace with their corresponding discrete element if you want to convert from the continuous to discrete time, except feedback signal. Feedback signal always should be represented by the help of the sampler. Okay, so that one. Now here we are simplified that block diagram into this one. So we know R of Z is reference input and E of Z is the error signal, and E of Z nothing but the controller output. We are calling it as a manipulated variable or control variable. You can call with any name. Okay, once we are passing to the system, so here I combine Hg of Z. So zero order hold plus process. We know why we are using zero order hold, because transfer function is 1, always 1. Pulse transfer function of zero order hold is always 1. Okay, always 1. So digitalize the plant with the zero order hold. So Hg of Z nothing but the digitalized plant. Now, so digital controller. So our topic here is to design the digital controller. Okay, this also we know the closed loop transfer function of the system. This also we know. Okay, you just assume this as G of Z. So D of Z, G of Z divided by 1 plus G of Z, G of Z. This already we arrived in the unit 2 and we have seen during the implementation of control algorithms. Okay, this is the digital transfer function, output by input, nothing but the pulse transfer function. Pulse transfer function. Okay, now the required controller is this one, D of Z. Okay, so we know we have this formula, 1 by G of Z, Y of Z divided by R of Z, 1 minus Y of Z divided by R of Z. So we know this formula. Here Y of Z by R of Z replaced with the T of Z. So 1 by H G of Z multiply with T of Z by 1 minus T of Z. Okay, ma. We are seeing everything known data. Okay, we can fast and if you stay, you can ask me at any time if you have any doubts. But please interact here. Please interact with this class. Now, this is the procedure if you want to implement any discrete control algorithm in MATLAB or LabVIEW. Okay, if you want to test your algorithm with the process given plan, so you need to choose any software. The software may be MATLAB or you can choose LabVIEW. You can choose LabVIEW, and we have one more, Scilab. I think all of you may heard about the Scilab. Okay, it's an open source software like Python. So you can implement all, you have the simulating blocks corresponding to the control system, signals processing, and DSP. Okay, so most probably we are preferring the MATLAB to implement the control algorithm for any process. Okay, so first you need to know the transfer function of the plant. So you need to derive the transfer function of the plant by using any mathematical equation. Okay, it may be from fundamental laws or it may be from law of physics or law of chemistry. Okay, once you know the fundamental laws of the system, you will arrive the transfer function of the plant. Okay, Now, second one, the transfer function of the system is converted into the Z plane. That means we want to convert continuous into the Z plane, Z domain. And third one, design a suitable control algorithm in the Z plane. So you can use any algorithm. You can use any one, Deadbeat, Dahlins, Kalman, PID, digital PID, whatever it may be, depending upon according to your application. So implement the control algorithm on digital computer. That means write the program in MATLAB. Okay, that means write the program in MATLAB. So this is the flow of process. If you want to implement any algorithm in the software. Okay, so for simplifying version, we have studied Deadbeat Dahlins in our unit 3. Okay, so here I consider two controllers. One is Deadbeat controller, another one is Dahlins controller. So I have considered these two, Deadbeat and Dahlins. Okay, so here we are going to see how the response of this controller algorithm with respect to different type of the process. Okay, we will analyze now in MATLAB software. So first you see Deadbeat controller is simple response. The principle of this one is very simple. A technique to achieve an ideal response but require excessive control signal. Okay, a technique to achieve an ideal response but requires an excessive control signal. What does meaning of ideal response? Set point. So it should track the set point as early as possible. Okay, the error dynamics will die out 0, but the controller output is have excessive peaks. Okay, that means the real-time industry people will not allow these excessive control signals. And comes to the Dahlins controller, a technique to approximate the deadbeat control, but does not require excessive control signals. So you could draw back into excessive control signals. So that should be eliminated with the help of the Dahlins control. అది కూడా ఎలా చేస్తాం మనకు తెలుసు by the approximation of parameter alpha f. ఓకే, ఈ పారామీటర్ మనం డాలిన్స్ లో చూసాం. ఇది ఎలా సెలెక్ట్ చేస్తాం? ట్రయల్ అండ్ ఎర్రర్ మెథడ్. ఓకే అమ్మా. సో ఫస్ట్ digital control, this is generalized formula we already have seen. Okay, earlier slide we know also this one. This is the d of z, generalized formula of d of z. Okay, now this is the equation. So you see this equation states that the required controller d of z can be designed if you know the model of the process g into h of z. So we should know the process model g h of z. Okay, that's one point. Another one is the controller d of z must be feasible. Okay, that is d of z must have a numerator whose order exceeds that of the numerator. Okay, sorry, actually this is the denominator. This is denominator, not a numerator. Okay, whose order exceeds that of the denominator. So whatever the controller you are going to design, that must be in the feasible mode. So here you just see one example we consider here for deadbeat controller. So deadbeat controller is one in which a step input is followed by the system. We know C of z is nothing but the z inverse. Okay, the output tracks the change in set point within one sampling period of time. This is the principle of deadbeat algorithm, but delayed by one or more sampling periods. So here we have z inverse, one sample period. The system response is required to be equal to unity at every sampling instant after the application of unit step input. So you see here the graph. So here we are trying to apply the unit step input at 0. Okay, at 0. Here we have the initial conditions also. Okay, because all the systems will exhibit the initial condition. So you should consider the initial conditions. So here the input is varying from 0 to 1 at 0. Okay, the input is varying from 0 to 1 at 0. Now you just see the output, how it's going to. So the output tracks the input after 4 sampling period of time. That is t is equal to 4. That means z4 minus 4. So it took the time z4 minus 4 to reach the set point. And then remains as a constant as provided in the input. Okay, so it follows the input. Okay, this t is equal to 4. This just like example. Okay, So here, from the above example, we have come to the picture T of Z is equal to Z power minus K. But deadbeat algorithm is different, deadbeat controller is different. So people should understand the difference between algorithm and control. Okay, algorithm and control. We know C of Z by R of Z. Okay, Z inverse. Z inverse. So C of Z by R of Z nothing but the T of Z. Z inverse. Z inverse is not applicable to all type of the process. So we want to summarize or we want to simplify the expression in generalized mode. So generalized mode nothing but Z power minus K. So K should be greater than or equal to 1. If K is equal to 1, it satisfies this equation, Z inverse. Okay. So the desired control loop, closed loop transfer function should be T of Z is equal to Z power minus K. Okay, ma'am. But in our practice, we have done with Z inverse. Okay, we have done with the Z inverse, but you have to replace with Z power minus K actually. So if I substituted in the controller equation, so this is my equation. 1 by Z power K minus 1. Okay, 1 by Z power K minus 1. But actually we have 1 by Z minus 1. Okay, there we will have only 1 0 at horizon. Here we have K number of zeros at the horizon. Okay, so generalized way. This is nothing but generalized way representation of any deadbeat controller. So now we have seen, this is the example. This already we have solved during the classroom work. During classroom work, we have solved this one. So we have considered this is the example. G of s equal to e power minus 2s divided by 10s plus 1. So we want to design a deadbeat controller for the system. Assume t equal to 1 second. Assume t equal to 1 second. Okay, I think how many of you remember, I don't know. So during problem solving in classroom work, we found that deadbeat algorithm is not suitable for time delaying process. Time delaying process. Okay, so that how you are going to prove in by using a software. So we will see here. So this and all we know. All these things we know because we know how to find the G into H of Z, Z transform of 1 minus e power minus Cs by S. So 1 minus Z inverse into Z transform of, this look like the 1 minus Z inverse into Z transform of Gp of S divided by S. So we know this formula, right? So if you expand this one, so you will have this continuous domain equation, then apply partial fractions. So apply partial fractions. So we have in the form of Z. So this is the final Z equation. Okay, now if you multiply this one, so this is nothing but the final G of Z. G of Z process transfer function is looking like this. Okay, this is a process transfer function. So I want to implement the control algorithm, right? So I am applying the formula here. Okay, I am applying the formula. So this is the G of Z. So once I am applying the formula, this is nothing but the G of Z. And this is nothing but T of Z by 1 minus T of Z. Okay, we have considered here generalized formula. So we have 1 by Z power K minus 1. Okay, now you need to find the K value. Okay, so we already seen one point for feasibility. Okay, the order of the denominator should be greater than or equal to the order of the numerator. If you see, what is the order of the numerator here? Sorry, once again. So what is the order of the numerator here? 3. So what should be the value of K? It should be equal or greater than 3. Then only the controller is feasible. If you can implement the control algorithm. Okay. Then only you can implement the control algorithm. So the order of the D object should have more than 3. So we are considering here K should be greater than 3. So you can say K should be greater than 3. Okay. So K should be greater than 3 means which one is minimum value? K is 3 minimum value. So we assume K is equal to 3. Now we substitute the value of K is equal to 3 here. Okay, this is my D object. This is my D object. Okay, controller. This is my D object. Now I'm implementing the control algorithm in the form of closed loop structure. So this is my control algorithm, D object, and this is G object. Okay, once I have the structure like this, so I need to write the program in the MATLAB. Okay, to analyze the discrete design system performance, let us simulate the step response. We are going to simulate the step response of the given closed loop system. Okay, so once after applying in the MATLAB, so I arrive the response is like this. I will show the response also. Okay. So as designed, the step response is unity after 3 seconds. Can anyone say why it took 3 seconds? Because the order of the system is 3. Okay, the value of k should be greater than or equal to 3. So it will take k seconds to settle. The output will be settled at input and stays this value. You can see here. So the output tracks the one at k is equal to 3. Okay, like this. Okay, all of you can see the circuits, white mark circuits. Okay, it tracks the input. Okay, ma. So here what is the important point is, if you want to implement in any real time, the response is correct only at the sampling instance. Okay, and the response can have oscillatory behavior between the sampling instance. We are not interested to see the response between any two sampling instance. You see here, we don't know the response of these two sampling instance of time. Okay, it may be oscillatory. It may be oscillatory. Okay, but we are not focusing on that one. Our point is now whether it's able to track the step input at sampling time. That's all. Okay, present instant of time. So we don't want to worry about that point. So now we have seen previous slide how the output tracks change set point. Now if it comes to this slide, how the controller will give the effect. You can observe here, initially at 0, we have the large controller output. See, why we have the large controller output? Because error is large. Error is large, right? So we know deadbeat algorithm will track the set point within one sample period of time. So immediately it will drop to the some value. It may be anything. So immediately drops some value. Then remains constant. It remains constant. So the control output remains constant. So here, what is the drawback here? So initially we have the magnitude of 11. Okay. So this is very high. At the beginning, if you have the control output as magnitude of 11, this is not acceptable in practice. Okay, ma'am. మనం ఏం చేసాం? మనకు అక్కడ ఏమొచ్చింది ఈక్వేషన్ లో we have m of n plus 1 or error of n plus 1 వచ్చింది. So we concluded that current controller output m of n requires the future error value. So deadbeat algorithm is not possible. But here you don't have like this m of n plus 1 or m of n minus 1 like this. Okay. One second, what happened? Close this one. Okay, leave it. So we don't have this terminology m of n plus 1 or m of n minus 1. We have only the current signal. But here the drawback is it's accepting it have higher magnitude, which is not possible in real time. These are the drawbacks. Okay, so this is the MATLAB code for what we have designed. So first see here, we have designed the transfer function. All of us know how to use the MATLAB, right? So we have seen simulation lab. TF is the command to create the transfer function. We have provided numerator and denominator, and delay term should provide with IO delay. So we are converting into the discrete domain. C2D is a command to convert in the discrete domain. Okay, then we have the poles of the system. Okay, so this is the GC. Once we have the GC, we are going to find the closed loop system. Okay, GCL is nothing but the closed loop system. Then you need to perform the step input. So step input requires the time signal. So this is the time 0 to 1, 0:1:10 corresponds to time signal, and you have applied the step input. Okay, that one you have plotted here and given as figure 1. Okay, these are all like decoration. You can give marker size because I need to identify where we are getting the output, right? So we are expressing the output with the symbol of O, and marker size is 6. So X label, Y label, X label, time, and axis. Axis we are providing because generally if you implement any MATLAB, so it will take from 0 to 100. Okay, axis will take directly from 0 to 100. So we are going to restrict from 0 to 10. 0 to 10. Okay, the axis will limited to 0 to 10. So tight step response. So this will give the process output. How PV variable reaches the set point. Then you need to plot the controller output. So control transfer function. Controller transfer function. So the same step input we are providing the controller response. So we are going to see the control signal. Okay, this is a MATLAB code for deadbeat controller. And similarly, we are going to implement the Dahlins controller. Okay, Dahlins controller. So Dahlins controller, simply we are calling it as a modification of deadbeat controller. Simply I can call it as nothing but the modification of the deadbeat controller. So which provides an exponential response that is smoother than deadbeat controller. Okay, an exponential response. So we will see what does it mean, exponential response. Okay, now we are applying the step input to the system. So it look like this. So it will track the response by this way, Okay, so we can find time constant, everything. So we are having the same closed loop system. This we have seen the mathematical model of the Dahlins algorithm. So we are considering there we have e power minus theta d s divided by tau s plus 1. Here the notation alone different. So here they are representing with e power minus ls. Okay, e power minus ls. Now I can substitute here and we are going to find Z transform. Z transform gives us the pulse transfer function of the system. So similar, we are considering the similar structure or similar plan what we have done earlier. That means with the help of deadbeat algorithm. Okay, so same plan has been considered here. Okay, so we are trying to implement the Dahlins digital controller for the same system. Time period also same, but here closed loop time constant is 5 seconds. All of us know what does it mean, tau f. Tau f is equal to 5 seconds. Tau f is equal to 5 seconds. Okay, this and all we know how to find this one, because so only I have not provided here. Okay, so g h of z is equal to directly we can write this one, because this we already arrived during earlier slides. Okay, in the example of deadbeat. Okay, next t of s. T of s equal to e power minus ls by 5s plus 1. Okay, so now we want t of z. T of z అంటే ఏంటి ఇక్కడ మన ఫార్ములాలో r of z divided by c of z divided by r of z. Output by input. Okay, so we are going to obtain the t of z. Here also you can see we are using z power minus k. But in the theoretical part, while we are solving the problems, we can set z power minus n. Here z power minus k. Okay, similar way ma idantha man notes to solve chesam. Everything is solved in notebook. So I am substituting here. We know g of z and we know t of z. So we are substituting here in d of z equation. Okay, so this is the numerator part and this is the denominator part. This is the numerator part and this is the denominator part. So now if you see, the order of the denominator should be higher than the or equal to the numerator. Okay, the order of the denominator should be higher than or equal to the numerator. So now you can see this here. So for the controller to be implement in real time, so the degree of the numerator must be less than or equal to the degree of the denominator. So what you have to consider here, you have two parameters, 3 minus k and 2 minus k. So which one will have more influence? 3 minus k. Okay, which one will have more influence? 3 minus k. Okay, so we are considering 3 minus k should be less than or equal to 1. Why we consider 1? Here we are already having the power 1. We don't know the value of k, but we have the power 1 in z in denominator. Okay, so 3 minus k should be less than 1. So this is very important one. So this point is important. 3 minus k should less than 1 and k is greater than or equal to 2. So in deadbeat algorithm, you have received k is greater than or equal to 3. In Dahlins, so the order of the k has been reduced with respect to Dahlins algorithm. So we are assuming k is equal to 2 because it is a minimum value, and we have designed the controller. Okay, and we have designed the controller. So this is the controller response, controller equation. Okay, now we know we have the g of z and we have the d of z, everything. Okay, so frame the closed loop structure and simulate in the MATLAB. Here we can see the response of the system process variable. You can see here. So the response tracks its point input in the form of exponential signal. So it increasing exponentially and reaches the value 1. Okay, but in the case of deadbeat, so how it reaches the response? In the case of deadbeat, suddenly all of sudden it reaches the response like this. Sorry. So all of sudden it reaches the output 1. That's all. But here we have the exponential rise. Okay, so what are the parameters will be influenced by this exponential rise? Time rise, time constant, settling time. Okay, so etc. Time domain parameters will be affected with respect to Dahlins algorithm. Okay, so these are the parameters will be affected Dahlins algorithm. Now comes to the control signal. In the case of deadbeat, you have 0 and you have 11, 10. So here we have the signal. Okay, control signal at initial value. But here you can see the maximum magnitude of the controller at n is equal to 0 is something about 1.9. You can see drastically how much it has been reduced. It's much smaller than the control signal which we have obtained during the deadbeat controller. Deadbeat controller, we have the value 11. Okay, so this value can be acceptable in the real time because the actuator valve will move like this. Okay, so it's smooth response, right? So people can accept this type of the response. Okay, so this will enhance the life of the actuators or plant or some etc. whatever it may be. Okay, so we are considering the Dahlins algorithm. We are considering the Dahlins algorithm. Okay, ma. So this is the way of representation. So here we have seen same MATLAB code for Dahlins algorithm. Same like deadbeat, we have framed the MATLAB code for Dahlins also. Okay, we have simulated in the MATLAB. So we arrived the response. And now we have considered the standard test input signals. So this is the 1 by s plus 1. 1 by s plus 1 is nothing but standard first order input with tau is equal to 1 and k is equal to 1. So this is the transfer function. So if this is the transfer function, okay, Simulink block, we have drag and drop the transfer function from Simulink. So we have inbuilt zero order hold, and this is the D object we have designed mathematically. We have designed mathematically, and we are imposing the step input to the process. Now you can see the response which I have shown in the yellow color. So this is nothing but the directly I took the screenshot from the scope. So this is the response of the system. You see here. So 0 to 1, there is no output. At 1 to 2, it reaches the set point. 1 to 2 reaches the set point. After 2, it remains as constant. Within one sample period of time, it reaches the set point. You can easily observe here. This with respect to 1 by s plus 1. Now I am considering 1 by s plus 1 whole square. All of us know 1 by s plus 1 whole square represents the second order system. Okay, second order system. Okay, so we have the zeta, we have the frequency, oscillation frequency, everything. Similar concept. So we have designed D of Z manually. So the D of Z has been incorporated in the MATLAB. So we arrive this response. Now you can observe here. Okay, the output response having the oscillatory response in order to track the step. Okay, so the response is nothing but the oscillatory. 1 by s plus 1 whole square. And next, similarly, I'm going for 1 by s plus 3 whole cube. 1 by s plus 3 whole cube. So here you can see now. So initially the magnitude is very high. The magnitude of oscillations is very high, which is not acceptable during real time. But mathematical deadbeat algorithm. So it can't applicable more than the first order process. Theoretical deadbeat algorithm can be applicable only for first order process. But here if you see second order process tracking, third order process also is tracking. Okay, so we have designed the controller by mathematically. So this is the controller equation. Okay, and so we have more oscillations. Here the point is I am assuming sampling time is equal to 2 seconds. Okay, if I am considering sampling time is equal to 1 or 0.01, I have arrived here more oscillations. That means the output took more time to stable at given set point. Okay, and this and all know ringing and pole placement. We know this concept. So ringing, we know where we are getting the ringing effect. The controller will have the pole set -1. The controller will have the pole set -1. Okay, and next one, Dahlins method. Till now we have applied the standard sickness. That means deadbeat for standard sickness. Now we are seeing how the same in systems will exhibit with the Dahlins algorithm. So here also we have considered 1 by s plus 1. This is a transfer function 1 by s plus 1, like first case in the deadbeat. Now you can see the order of the Dahlins algorithm has been reduced and it will have smooth response. It will have the smooth response. Okay. Dahlins algorithm method will have the smooth response. Now you can see here. Now second order system. I am assuming second order system 1 by s plus 1 whole square. So this 1 by s plus 1 whole square, I am assuming as tau f is equal to 0.35. Tau f equal to 0.35 and we have designed d of z like this. D of z. So we arrange the d of z. So if I plot the d of z, I didn't get the output as stable at set point. Why? What may be the reason? Because of the wrong chosen of tau f. So I have chosen wrong value. Tau f is wrong. So if I change the value of tau f, then I may get the set point tracking. So this has not been settled. It's continuous further. This is the controller response. Controller response. This also is not acceptable in the real time because keep on is increasing, right? So this is also not acceptable in the real time. So we can say that till now what we have studied, deadbeat algorithm alone is not acceptable in real time. But here we have seen when I am trying to apply Dahlins method for second order system, the response is oscillatory. Okay, so which causes the excessive peaks. This also is not acceptable in real time. So final conclusion. So okay, so we'll come to the next one. This is the third order. See, and similar what we have studied 1 by s plus 1 whole cube. 1 by s plus 1 whole cube. Then d of that implement cheste. You see, the order is 4 only. As compared to the deadbeat, the order is reduced only, but it has more oscillatory response. With more oscillatory response having high positive and low negative value. So this response cannot be acceptable by any industry. Cannot be accepted by any industry. So to compare with the deadbeat, I am considering t is equal to 2 here also. Sample time is equal to 2. Okay, so from this, what we have come to the conclusion is you can apply any method, deadbeat or Dahlins, to any real-time process, but you should know the knowledge of the process. Sometimes deadbeat may give satisfactory response, and sometimes Dahlins may not give satisfactory response. So this is not satisfactory response. So I can go prefer for the digital PID, or I can prefer the Kalman's estimation method. So I can have different type of the algorithms. Okay, ma. So ఈ స్లైడ్ నుంచి మీకు ఏం చెప్పాలనుకున్నాను అంటే డెడ్బీట్ అనేది మాత్రమే అప్లికబుల్ కాదని చదువుకున్నాం. కానీ ఇప్పుడు ఏంటంటే Dahlins also may not give some satisfactory response in the point of performance point of view. Okay, so we are not in a position to conclude that which algorithm has not give satisfactory response. It entirely depends upon the process knowledge. Okay, entirely depends upon the process knowledge. Okay, and digital PID comes to the digital PID algorithm. So till now, till this one, and we have studied about the deadbeats and Dahlins. Now you may ask the question, so why you can't implement the Kalman's? Kalman's algorithm is entirely different, so it requires additional some mathematical knowledge if you want to go for the Kalman's. So it may get confused to you. So I have not included here Kalman's. We have considered only deadbeat and Dahlins. So digital PID is very simple. We have seen, and this is the controller, PID controller, and this is our transfer function. Okay, simplified block diagram is like this. Okay, d of z and g of z. Okay, we know the d of z. So now, so this is the g of z. This is the g of z. 1 minus z inverse by 1 minus z inverse multiplied with z transform of g of s by s, and d of z is taken to be PID controller. So here we are assuming that d of z is about the PID controller. So PID. So here I have given two parts. One is continuous domain, how it look like, and discrete domain, how it look like. So this expression gives the proportional gain at continuous and this as discrete. So we have only the constant Kp and Kp. Okay, we have only the constant block, and all of us know what is proportional, derivative, integral. So no need to go for the explanation. Just I have given the terminology with respect to the continuous domain. This is derivative term KDS, and we know KDS. How we are going to replace in the derivative like this: KD into E of k minus E of k minus 1 divided by T. Okay, now we have seen until this part in mathematical representation of digital PID. Now what we have done here is, so E of k I am assuming as 1. And what about E of k minus 1? So the error output delayed by one sample period of time. So how we are going to represent one sample period of time? Z inverse. How you are going to represent one sample period of time? Z inverse. So E of k is 1 means E of k minus 1 nothing but the Z inverse. So I am replacing this terminology. 1 minus Z inverse by T. Okay, so if I simplify it, we have this one. KD Z minus 1 by TZ. Okay, ఇది ఒక్కటే మీకు కొత్తగా ఉంటుంది. Okay, and similar like integral controller, Ki is the continuous domain. All of us know Ki integral of T naught to T et d dot et dt. So discrete time వచ్చేసరికి we are replacing with the help of summation, right? So E of k minus 1 plus Ki into T E of k. Okay, T E of k. This we have seen in the derivation of position PID algorithm. So we know E of k. So we are replaced here. So this is the D of Z, integral controller. Okay, integral controller. Now we know integral controller and derivative controller and proportional controller. You can combine all these three. So if you combine all these three, this is the digital PID controller. Digital PID controller. Now you can see how much big it is. We have not seen earlier. So Kp plus Ka plus Kd Z square minus Kp plus 2 Kd Z plus Kd by Z minus 1. So if you want to implement PID algorithm in real time, you should use this equation. And this is nothing but the digital PI. PI and time was P plus I. So Kp plus Ki. And PD, P plus D. Kp plus Kd. Okay, so we have the transfer function of PID and PI and PD in discrete mode. We have everything, transfer function of PD, PID and PA. Okay, now I am expressing in bilinear transformation. Okay, why I am expressing this one also I will say. So I have the continuous time equation. This corresponds to the PID in continuous domain. So once I replace S with 2 by T, Z minus 1 by Z plus 1. All of us know this is nothing but the bilinear technique. So if I replace with S with bilinear technique, so I have these parameters. Alpha 2 Z square, alpha 1 Z plus alpha naught divided by Z minus 1 by Z plus 1. So here alpha naught, alpha 1, alpha 2 are the design parameters. So ఇప్పుడు ఏం చేస్తామంటే మనం ఈ digital PID controller, when I substituting bilinear, we have one equation that should be compared with this one. So if we compare with this one, we have alpha not this one, Kp plus Ka plus Kd is nothing but the alpha 2, and alpha 1 is nothing but the Kp plus 2 Kd. Alpha naught is equal to Kd, and we have Z minus 1 by Z plus 1 in the denominator. But in the case of here, digital PID, we have Z by Z minus 1. So always one pole is existing at the horizon. If you are implementing digital PID conventional algorithm, one pole is at horizon. But if you are implementing bilinear transformation algorithm, we are not having pole at horizon. So we have the pole at Z is equal to plus 1 and Z is equal to minus 1. Okay, which frames the radius circle. If you are implementing the PID controller using bilinear transformation. Okay, so there is a deviation between these two, but currently it's not required to you because I have tried to give differences between these two where it has been differed. Okay, I think I hope all of you understood this one. This is nothing but the direct PID algorithm which we have arrived from the discretized equation, and this is nothing but the conversion PID. We have the PID equation in continuous domain, that there S should be replaced with 2 by T into Z minus 1 by Z plus 1. So we consider an example, very simple example. Okay, first order system 1 by ms plus b. I have considered a car, for example, BMW. Weight is 1000 kgs and coefficient friction coefficient 100. Okay, so I am going to design a cruise control system, and car can reach the 100 kilometers per hour from 0 kilometers per hour in 8 seconds with an overshoot of 20%. Okay, with an overshoot of 20%. So assuming sampling period is equal to 0.6. Okay, now I have this can be represented as 1 by ms plus b. So we have g of s, m value, b value. We are expressed here, and you find out the discretized pulse transfer function g of z. So g of z is like this. And now I have the equation. First I am applying here PI algorithm, PI controller. So PI I am substituting here. So this is a closed loop structure, right? So you can frame g of z h of z divided by 1 plus g of z into h of z. So there we have the big equation h of z. Okay, we have the big equation. So unknown parameters is kp, ki is our unknown parameters. Kp is ki is our unknown parameters. Okay, and PID algorithm. So I'm substituting replace PI with PID. Okay, PI with PID. So we have one more equation like this. Now, how we are going to calculate the KP and K? How we are going to calculate the KP and K means the PID algorithm look like second order standard equation like this. Omega n square divided by s square plus 2 zeta omega n is plus omega n square. Now, if I am equating these two, I am arriving the KP and Ki value. I am arriving the Kp and Ka value. So zeta omega n b omega zeta omega n. Now you may ask question. So how I will get the zeta and omega n? They clearly they have mentioned, right. Settling time is equal to 8 seconds. Overshoot less than 20%. So you have the formula. You substitute here and you have the kpk value. Then you can substitute here and you have the tracking response. So like this you have to design the PID controller. Like this you have to design the PID controller. So I will try to simulate the deadbeat algorithm in MATLAB. So which we have written here. So now you can see this output. Deadbeat. So like this you have to implement in if you want to go for any algorithm in real time means you have to follow this procedure. Okay, and you can simulate same response in LabVIEW also. LabVIEW also it is possible. So now you can see here this is a step response. So I think you can able to see the position here. So this is a step response 0. Okay, it tracks the set point after t equal to 3 because we have z minus 3. And you can see the control response is we have magnitude 1 plus or 11, so which is not acceptable by the industry. Okay, so this corresponds to the deadbeat. And similarly we have the Dahlins. So similar process I have considered here. So similar one. Now you can see. Okay, here we are using command state command. Okay, to just to know the way we have the output. So like this, the Dahlins response will have the output like this. So it tracks the set point, and this is the acceptable control signal. So people will acceptable this type of the control signal. Okay, so like this, if you want to implement, so you can do in the real time. And I have shown here some documents related to the digital control system. So this is the very basic one, and which have been published earlier 1970s. So this is PID equation. So they have considered continuous time domain and the PI and PD. Then we are moving into the discretized version. Okay, discrete version. They have given how to calculate the changing control algorithm in the case of velocity algorithm. మనం చదువుకున్నాం two algorithms, velocity and position PID. Okay, so velocity algorithm, how they are calculated in the controller response u of k minus 1, because you need to perform everything in simulation. So this is the response of the system with respect to the step input. And what are the problems they have occurred during the implementation? Derivative kick and integral wind up. ఇది కూడా మనం చదువుకున్నాం, derivative kick and integral wind up. Okay, these are the problems occurred for position PID algorithm. So this is the Simulink block. simulating block, and they have simulated in the MATLAB, and they have calculated PID with the help of Ziegler equals tuning rule. మేము ప్రాసెస్ కంట్రోల్ చదువుకుంటాను. We have standard tuning rules for PID, Ziegler equals, Cohen-Kuhn, Lou-Benz method. We have a number of techniques. Okay, so they calculated from here. So now they replace the digital PID instead of D of Z, and they are the response. There is a response, tracking response like this. Okay, here they implemented both Deadbeat and Dahlins algorithm. Deadbeat and Dahlins algorithm for different set point input. Okay, I will forward this material to you. If anyone have interested, they can see this one. Okay, and one more thing is, so how you are going to implement the MATLAB. So this was published in the Russian university. Okay, Slovak University of Technology. So Russian people have been working on this one. So discrete controller, and they consider the second order system as a case study. Second order system nothing but electrical furnace model. They have implemented the discrete system for electrical furnace model. Okay, so this is the electrical furnace model, and they have the pulse transfer function. So these are the different methods I told you, right? So we have a number of techniques to frame the controller equation: stable TOC, finite TOC, constraint finite TOC, feed forward, quadratic controller, deadbeat, constraint deadbeat. Because you should use which one will be gives the satisfactory response. Okay, so these are the research papers actually. So now we can compare the responses of all other controllers. All controllers are satisfying the servo response. It tracks set point change. But what are the deviation here? So some controllers may give oscillations, and some controllers may increase the settling time. So like this. So which one will be useful for us? That one will be you have to use. See the controller action here. Controller action. So quadratic controller have given the large controller error, large control signal. This is always not acceptable. And rest of the controllers will have same type of the similar type of controller action. So we can use any other one according to our specification. So they have given here time domain parameters. So they calculated everything and they have given here. So here they have used the MATLAB. So this is about the MATLAB version. So MATLAB we have deadbeat algorithm. Inbuilt we have deadbeat algorithm. No need to write the code also. You have deadbeat and Dahlins simulating block. Directly you can paste your what we can say that is transfer function. And this is nothing but how to determine the Dahlins algorithm parameter. So we know alpha f is a unknown parameter. So we are going to find alpha s by using trial and error method. But here in this, the author have provided the method how to choose alpha f with respect to your process. This is very knowledgeable and very important paper. Those who are willing to work in digital control algorithm, they should refer this paper. Okay, so very easy. Here you try the CSTR system. I think all of you know about the CSTR, right? Control system and instrumentation people will know about this process. Continuous stator tank reacting process. Here I have provided open loop response, how we arrive at the Dahlins algorithm, and how we can track the set point. Okay, so these three are basic paper. And one more thing I am going to show here is one of the author, he implemented the discrete algorithm for non-linear spherical tank system. Instrumentation people, non-linear spherical tank level process. So he has the setup like this. So I am showing the setup alone. So implemented in the lab. So he has the setup in his lab. Okay, like we have also having setup in process control lab. Okay, we have 2 tank, 3 tank, 4 tank system, and spherical, cylindrical, conical tank, heat exchanger. Everything will be integrated and connected to DCS. So if anybody is interested, they can come and they can work on any type of the process. Okay, they can have one publication. So research publication is very important. Those who are willing to continue their studies. Okay, so this is the, until you have any doubts, unit 3. So if you don't have doubts, enter your roll number in the chat box. Those will be considered for attendance. All of you enter your roll number in the chat box. Now, meanwhile, if you have any doubts, you can ask me. related to anything or generalized doubt, unit 3. So what is my motive is you have plenty of problems. You have a number of problems to work on control algorithms in discretized domain. Okay, control systems ki future undi. I want to convey this one. Okay, ma, those who are given attendance, they can leave the class if they don't have doubts. Attendance ఇచ్చిన వాళ్ళు they can leave the class, ma, if you don't have any doubts. Otherwise, you can ask doubts. So try to concentrate on this thing, and you can implement any small part in your project work. So next class we will see the unit 4. All of you, please give attendance. Rest of the students. Others, please give attendance. I am going to close the session. Others, give your attendance. Others, please give your attendance. I am closing the session. So you people are not in the class. Okay.
సార్ 90 పోయింది సార్.
అక్కడ రాయండి మా చాట్ బాక్స్ రాయండి మా అదర్స్ 21 ఎర్లీ 21 70 అటెండెన్స్ ఎంటర్ చేయండి మా.
సార్ నాకు చాట్ బాక్స్ లో కీబోర్డ్ టైప్ అవ్వదు సార్.
కీబోర్డ్ టైప్ అవుదా? 98
98 సార్.
ఓకే అమ్మా, ఓకే, నేను ఇస్తాను
సార్. ఎంటర్ చేశాను సార్.
ఓకే అమ్మా, ఓకే మా 70 55 ఓకే.